Previously, we set up a basic FEM simulation. In this case, we're dropping the rubber toy model onto a ground plane. I'm not going to be covering a great deal of this type of simulation at the moment. The Vellum soft body functionality does overlap with this kind of simulation. We will look at some of the aspects of this though. However, in my case, the main focus for looking at FEM is in terms of rigging. Because we're going to be focusing on rigging, the next thing that we look at is not going to be this style of simulation. Instead, we're going to look at how we can apply FEM to an animated mesh. So to start with, we're not going to work with the rubber toy. Instead, I'm going to work with a simple tube. This will allow us to simplify the setup. We can view the result of the setup of the bone deform node. This is a very simple setup with basic animation applied. Here we have a tube. We have a line which is being converted into a rig. The conversion is being done using a rig doctor node, and we have a basic animation being applied in a rig pose node. For the weight, we have a simple biharmonic setup, and this is a default weighting setup. We then view the output of this in the bone deform node. First, we'll want to bring this animated mesh into our simulation network, and we'll want to use it to drive an FEM simulation. The second thing that we want to do is have this simulation drive another mesh. In this case, we have a second tube that we will try to drive with this simulation. So we're going to be looking at how to use animation within an FEM solver. We'll then look at using that animation to drive other objects within an FEM solver. We can now work on the network for the bone deform. So the important parts of the network to consider are our mesh and the weights which we are setting with the biharmonic capture. We're going to need to export both the weighted mesh and the deformed version of this mesh. To reference these, I'm going to get a couple of nulls. The first null will be connected to the output of our weight node, specifically in this case the first output, which is the actual geometry. This will give us our rest position geometry. I'll call this deformed mesh static. So this is the first mesh which we're going to need to reference, and we will then want a reference to exactly the same mesh with exactly the same topology, and this should be connected after our bone deform node, as this is where we'll have the animated mesh. I'll call this null deformed mesh animated. We'll need to refer to the mesh after it has been deformed. This is what will give us our animation, and we'll need the mesh before animation, as this is what the initial simulation will be based off. This is actually the geometry being simulated. For this to work, we will also want to have exactly the same mesh for the initial geometry as for the deformed geometry, and all the attributes on this mesh should be the same. So the point at which we create the tetrahedral mesh will have an influence on how well this node will work. I'll need to convert this into a tetrahedral mesh, and I'm going to use a tet conform node to do this. I'm going to connect this after the weights are added. This will actually give us issues. There are a lot of things that will result from the order in which we connect things, but it is easier to show these differences by doing the wrong thing first and then doing the correction. This will still work, but it will not give us ideal results. So by default in this case, we'll get a reasonable tetrahedral mesh out of this, but it's not a particularly good one. For this mesh, we really should be rating the detail, but that is not really required for this simulation. This mesh will then be passed into the bone deform node. We're not going to calculate the mesh after deformation, as that would actually lead to a new mesh being calculated every frame. For this to work, we want the points to match between the animated mesh and the deformed mesh, so we will not generate separate meshes at any point, which means that the mesh which we create must be created before the deformation. We should see that our deformation actually occurs, although we have some issues showing up in the viewport. These are relevant, but I'm going to ignore them for the moment. When we look at the final output, we will see that we have a tetrahedral mesh, and this is being deformed correctly. So we have our tetrahedral mesh, and we have our static mesh. For the simulation, I would not be using the original mesh at all. If we want to use the weights from the original mesh, we will need to connect the tetrahedrons in this order. This is one of the things to think about, as our original mesh will probably have different weights from our tetrahedral mesh. This is not something which should cause issues in practice, but it is something to keep in mind. We can now enter our DOP network. This network already has an FEM solver within it, and this is connected to a merge node. This node feeds into the output. To get our mesh, I'm going to use an FEM solid object node. I'll connect this to the merge node. We will be working in the deformation tab, and we'll get the mesh by referring to the deformation static null. We'll then have this static mesh refer to a target mesh. This will also be on this tab, it will be under the section called Target. The field will be Target Deformation. Here I'll refer to the animated mesh with ... deform mesh animation. So this will connect our meshes, but by default nothing will happen here. So in order to get this to work, we will need to increase the target strength. We will need to set this value extremely high. This will usually be between the millions to tens of millions. If I now change our frame, we'll have a simulation, and we should see that the mesh is bending with the animation. In this case, we're getting a bending which is not the same as our original mesh. This is partly due to target strength. However, in this case, the fact that the bending isn't matching is due to our mesh and not our strength. We can, however, get this to work better by raising the strength. I'll raise this to the power of 10, which will make this significantly larger. In this case, this will be 10 billion. This will give us a far more accurate deformation, but we'll notice that there's more deformation of the mesh itself. The reason this is happening is because of the order in which we set up our nodes. We have created the mesh after it is weighted, and this will affect the distribution of the weights amongst the points that we're creating within this mesh. The weights on the points that we have created will be interpolated, but this is not always going to give us the best deformation. To take a look at this, we'll work on a slightly updated scene. I've lowered the radius of the tube a little bit. I've got the base deformation set. The target weight is set to 1,000,000. I'll return to the original network. Here we're going to move the TET-conform node so it will add the mesh before the weights are added. The distribution of the weights here will actually be very different from what we got when we added the tetrahedral mesh after the weighting. Essentially, we'll get a much better distribution of the weights for the deformation of the mesh. This is based off the biharmonic distribution rather than a more simple linear interpolation. I should now be able to return to the simulation, and I'll resimulate the mesh. If we look at the simulation now, we'll see that the simulation matches the final mesh far more closely. Here we have a much better deformation. The root and the effector of our simulated mesh match the root and the effector of our deformed mesh. We have far more bending, but that is one of the things which we expect from the default setup of a soft body solver. This bending is what we wanted to get, and it's what we want to control at a later stage. This is something to pay close attention to when using animation for an FEM simulation. When the weights are added to the mesh will have a huge influence on your solve. The settings and the quality of the solve will change greatly depending on when you add the weights. We now have an FEM solver being driven by an animated mesh. Next, we want to use this to drive another mesh.